And thank you, webinar participants, for taking time out of your busy schedule to be with us here today to talk about aerospace and cable for industrial applications. This is a little bit of a different presentation. We haven't rolled this out a whole lot. So I will, without further ado, I have to talk a little bit about an intro. We've been around since 1951. This is not a new technology. We're 70 years into it. We've got 5, 15, 25, 35, 46, 69, and 115 kV. We're in all 7 continents, over 75 countries. We have continuous development, continuous improvement in our R&D department, and we're installed for reliability, economics, safety, and we always say it's a design option. It's not necessarily for everywhere. So we'll see where it is for. Very quickly, what is spacer cable? It's heavily covered, non-shielded phase conductors held together and supported by a high-strength messenger cable and connected to spacers every 30 feet. You can see the messenger up on the top there. That's a mechanical support member. It holds everything up in the air. It's also a system neutral. It's also a lightning shield, and it holds everything off the phase conductors that may fall on them from on top, whether that's trees or what have you. You see we've got a spacer every 30 feet, every 10 meters. A couple of brackets, a tangent bracket, angle bracket, dead end bracket, and that's it. It's a very simple system. Talk about the theory. I just have 3 slides. Basically, when we're using bare conductor, we're using air in between those phase conductors for the insulation. Air is a halfway decent insulator, but we need a whole bunch of it. So we need to keep a pretty large separation between those phase conductors. But even though we do have a good amount of insulation between those bare wires, we're still subject to outages due to, contact with trees, animals, etc., or phase conductor to phase conductor contact. So what we do is put a little bit of polyethylene on that phase conductors, and the poly, which is a much better insulator, it replaces most of the air, so we can bring those phase conductors closer together and still have a very high BIL, a high 60 hertz withstand, and that cable will withstand short-term phase-to-phase contact, phase-to-ground contact, phase-to-tree contact without suffering a fault. And the 3-layer insulation system is the first. We're going to have a semicon, and that semicon is going to be the same reason we use a semicon layer on underground cable, so that when I have a short circuit or ground on the outside of that outer jacket and full voltage stress across the insulation wall, that semicon will put the whole outside of the individual strands as well as the interstices at the same potential. So we smooth out the electric field, minimize the partial discharge, give us a higher BIL, and give us a longer useful service life. The second layer you can see is a high molecular weight, low density polyethylene. It's very soft. It gives us a high BIL. And it's also, we're using it soft because we want to be able to strip. We can talk about that a little bit perhaps in a different section. The outer jacket is the high density polyethylene. Now this is where most of the tricks are. We source the highest density, high density we can get, because there is the anticipation that at some point in time it might contact the tree and suffer abrasion. We want to have a very high abrasion resistance. Secondly, we put the UV inhibitor in that outer jacket, and that UV inhibitor is a chemical UV inhibitor. It's not fugitive, it's not carbon black, and it puts an umbrella over the carbon chains, so I protect them from the sun. It's where we put our track resistant adder, and that final layer is also where we put the color. We can either have black or gray, and they're used in different scenarios. And of course, due to Ohm's law, as I increase my voltage, I want to limit the charging current on the outside of the jacket. So I need more insulation. So at 15 kV, I've got 75 mils plus 75 mils for the 2 layers, which gives me about 3.8 millimeters of total wall thickness. Whereas when I'm up at 69 kV, I have 250 mils plus 250 mils for the 2 layers, 500 mils, half an inch, about 12.5 centimeters. So that's a lot thicker, if you will. Just run through a couple of quick applications before I get to the industrial stuff. We're using spacer cable in many ways for storm hardening. You know, here you see a tree has fallen down, it's hit the spacer cable, it's broken everything on the pole. Somebody drives by at some point and calls the utility, says, hey, there's something wrong here. They come, they cut the tree down, they lift that bundle back up with the equipment handler, put it on a new bracket, and they're done. They've never had an outage. So this is everything to do with reliability, quality of service, minimizing safety and SAIDI. And we've got dozens, hundreds of these photos. Here's a tree on a 69 kV transmission line, no outage. This is one of the famous national parks in Canada, where they can go in there and in a winter, and you can see you've got 3 trees lying on the messenger for the whole winter, no outage. They go out there in the spring, take those trees off, still no outage. So that's what we want. We also want to minimize our tree trimming. We're saying that we've got about an 80% reduction in tree trimming and saving fully 80–90% of the canopy. You see on the left, we've got a bare wire. They've cut that thing quite significantly, whereas on the right, we're stringing that spacer cable below the major limbs. We're not having tree trimming. We're not having outages. We're not having dead birds and squirrels. We're getting shade over the tree. We're protecting the houses in the neighborhood from the wind. It's a win-win from a reliability, economics, a safety, and public relations standpoint. Couple of other applications: commercial alleyways, backlot construction, road widening. Here's a typical situation, and this is commercial, but this could be industrial as well. You've got a 5 to 15 or 25 kV upgrade. National Electric Safety Code, or CSA, you can't fit it in the alley once you go to 15 kV. So you just install spacer cable. And we've got, you know, lots of these projects. Here's a substation exit. We're going down a residential alleyway. The only way you can do that is underground or with spacer cable. We've got multiple circuit applications, you know, 2 to an unlimited number of circuits on the pole. Maybe we're doing a transmission line underbuild. Here we've got a, you know, Duke Power, 230, 345 kV. We've got the 235 kV lines. We put on the same transmission structures. Here we've got a 132 kV bare wire up top, 15 kV bare wire below. We put 69 kV spacer cable. So this is a ring bus around a city, a municipal in the state of Louisiana. And then as far as talking about multiple circuits or substation exits, we're using a lot in renewable facilities, whether they are wind or solar, and now with the batteries being added. So here is a site where we had 550 megawatts. We brought it all back to the substation with 11 circuits, each carrying 50 megawatts. And we got it on 2 pole lines. And here we've got 9 circuits on 1 pole line. So there's really an unlimited number of applications you can use spacer cable for in industrial facilities. When I talk about specifically industrial, we are involved in a number of separate industries, so, you know, being mining, petrochemical, whether or extraction, or refinery or storage. We're at some of the pulp and paper sites, both in US, Canada, and abroad. We've got large industrial, automotive, high reliability, where you're manufacturing semicon trips, military bases, and transit applications. And some of those high contamination situations you would have would be Shell Oil in Arkansas, International Paper, Fraser Paper in Canada, Georgia International Paper, petrochem sites, Getty Oil, and scores of major industrials, whether that's Intel, Ford, Volvo, Denso, if you will. So starting with our high reliability applications, these are, again, where you're making semicon chips. Here's one of the facilities in the state of Oregon. They can't have outages, so they have to have multiple feeds. Even if you have a voltage dip for 5 seconds, you're going to reject $1 million worth of one lot of semicon chips. So they have to have high reliability. They can't have even momentary trips on the breakers. Then we get into, say, grain and storage. So here, well, for us, National Electric Safety Code requires 5. Okay, somehow I got muted there for a sec. I hope you can still hear me. So, for grain storage sites, we've got a limited right-of-way, and it's an extreme fire hazard. So these really tiny grain particles are flammable. Spacer cable will reduce that right-of-way and entirely eliminate that fire hazard. And here's another similar site where we're using double circuit into that facility. We also have transit applications, whether we're at New Jersey Transit or Metra in Chicago, Amtrak and New England, and some other facilities in South America and other locations in the world. You can see it in the up left there. It's a very small right-of-way, not threatening, quite safe. We have other industrial applications, whether they're high reliability. We've got multiple circuits. We have the avoidance of underground construction, whether we can't build underground, there's no space there, there's too many underground facilities already, or it's just too darn expensive. And then the economic aspects, as well as the flexibility. We'll talk about that briefly. If we get into mining, here's one of the more common situations where you're bringing a power line into a site that may be changing. So here's Acero Escondido in South America, if you will, in Chile. Here's one of the many mines we've done in Canada. In the US, this is Half Mile Lake and Brunswick mines. This is a nickel and molybdenum mine. So it's a very, very high reliability. We were told by the operations people there that if they have a fault, everybody has to leave the line. They lose 8 hours of production. If that fault isn't put back on inside that 8 hours, they lose another 8 hours of production to the tune of, I forget what they told me, $250,000 an hour or $250,000 a shift. It's a rather significant penalty for poor reliability. This is another mine we did in, this is Val d'Or in Quebec. It's called Canadian Malarctic. It's a gold mine, if you will, and there's tons of OSHA and mining safety and health regulations, as well as in Canada, as strict as the US, if not more so, that we've got to get power down to this mine because those shovels operate on electricity. They're not diesel or anything like that. So we have to get power down to a portable substation, which is on sleds. So there's the portable substation we have to reach. And this is a rather significant mine. So we had a project whereby we were able to bring spacer cable down to that portable substation on a sled, as well as have the ability to move that line when that sled moves, because there's only so much blasting you're going to do and pick up all the raw material with the shovel before you have to move that blasting location. Here's another mining project we did. This is the second large copper mine in the world. They do copper, gold, and also, I believe, molybdenum here. This is First Quantum Minerals in Panama. And this site, I want to say, takes up well over 100 square miles of real estate, and all the lines in this mine are spacer cable for economics, for safety as well, and for reliability, obviously. We had a lot of challenges in this site. Not only was it virgin jungle we had to go to, there's a lot of wildlife here. There's a lot of rough weather. There's also contamination. Mining sites in particular are contaminated because we have metal products flying around, sitting on the insulators and turning those insulators into conductors. So we really have to have clean insulating surfaces. We've got super high reliability. When you're taking gold out of the ground, you don't want to take a break. Minutes or money. We had areas where we had, say, here is a 2,000-foot crossing, very difficult to do with bare wire and would have been impossible to do with underground cable. We have safety. There's trucks driving around here 24/7, 365. And there was also an issue for economics. So very happy with the way this worked out. Another application that people really don't realize, and I won't dwell on this because this is not a mathematics tutorial here, but talk about voltage drop. How do we benefit when we go from bare wire to spacer cable? Well, what we're doing is reducing the space between our individual phase conductors. We're going from 6 or 8 or 10 feet down to 12 inches between those phase conductors. As we reduce the phase conductor distance, we reduce the GMD, the geometric mean distance, and therefore we're reducing or eliminating, canceling out the mutual inductance portion of the total impedance. So we're reducing the total impedance by 15 to 20%, which means I'm going to have 15 to 20% better voltage regulation than bare wire. I'm going to have a 15 to 20% better end of line voltage on voltage limited feeders, on any feeder. I'm going to have a higher power factor. So I'm going to have an X-on-R ratio closer to underground cable and bare wire. I'm going to still use reactive compensation cap banks, but they're going to come on less than bare wire or tree wire. And the voltage regulators at the sub are going to be operating less frequency. And very important in mining and processing facilities is that we have large motors starting inrush current that creates a significant voltage dip. So that's going to be much less of a concern when we're using spacer cable. We don't want to trip those motors offline with the voltage dip. And here, again, we're talking about long feeders. We're worried about the voltage profile. Crushers may be tripping offline with voltage inrush, but with current inrush and voltage dip. So that's one application there. So we can switch gears slightly, not that much, but talk about petrochemical sites. So they need high reliability. Again, we're taking oil out of the ground. We don't want to take a break. Oil, time is money. So we need high reliability. We also have a safety or a fire hazard. And petroleum sites, we need to avoid sparks because sparks create an issue where we might blow up the place. We have, as usual, always reduced clearances. Quite possible multiple circuits. Petroleum facilities take a heck of a lot of power. And obviously the economic aspect. So we've done a lot of petroleum sites, the petrochem sites. Here's an extraction site. This is in the Ecuadorian Amazon. Their whole facility there is switching over to spacer cable, and that's a very impressive facility. Now we go into refineries. So we've got, this is Petron in Bataan in the Philippines. 100% of their transmission lines are spacer cable, and this is a lovely facility, if you will. Then we have, we had extraction, refinery, and now we're going into storage. So this is a big thing in the US. We're also doing outside in Indonesia, Malaysia. Here is, this is Costa Rica. This is a refinery and a tank farm in Costa Rica. And that's for, again, safety and economics and reliability. We're also doing a lot of this in the US down in Houston. This is the Aubrey-Sylvie EPCO Ranger 2 site. It's storage. It's also a shipment area. And it's, again, amazing how much power they use at these sites. There's another refinery and storage site. This is an Enterprise in La Porte, Texas. And you can, I apologize for the smoky looking photo there, but you can see where the transition from spacer cable takes place. It goes into traditional underground cable termination on those cross arms there. And it goes right into a standard cable tray that you would anticipate using at a petrochemical site. So that's a nice transition. Then we have what we call a facility or capacity expansions. Industrial sites don't seem to have a whole lot of extra space on site. So those sites may require expansion if the business is expanding itself, or may require more capacity for bigger motors. There's really no physical room. Overhead bare wire lines or safety are dangerous. They're always a safety issue, whether it's pulp and paper or storage or what have you. And the underground cable option may be difficult. It may be impossible. There's a myriad underground facilities existing, cables, pipes, water, gas, wastewater, et cetera, et cetera. Let's take a quick look at a project that was done in the last year or so. This is a major packaging facility, one of the largest packaging facilities in the world. They needed a 100 megawatt expansion, didn't have room. They had basically had room for one building. They were limited to 15 kV feed. It would have been better to bring it in at 35 or 69 kV, but they were limited to 15 kV. It was impossible to use bare wire. There was no room. There were safety issues. It was not really viable to use underground cable. The facilities were already massively crowded. It was a super tight right of way that they had. They had to keep out of lines of, keep the lines out of the utility right of way. They had to keep the lines out of the street. They had to keep the lines safely from buildings. And again, the physical constraints were nearly impossible. So what happened is the utility built a new substation. You can see the substation there in the back. And they were really, you know, as soon as we got out of that sub, we're coming over the utility parking lot right into the facility. So we put 3 spacer cable lines on 2 poles. So we had 6 circuits on 2 poles. Those lines connected directly to the substation bus. And at that point, we started traversing the parking area. As we got closer to the facility in question, we merged those 6 lines onto a single pole line, and that would result in a vast reduction of that 100 megawatt feed footprint entering the facility grounds. We dead end those 6 circuits on 2 structures outside of the facility, and we transitioned to underground cable at the risers. And you can see we entered the facility on, again, standard underground cable trays. And those, yeah, that may look complicated there, but it's basically, you know, regardless of what kind of facility or how many circuits you have, it's a simple dead end. We're bringing those covered conductors through dead ends down to the cable termination. Yes, we have a surge arrestor there, and then we go right into the riser. So it's a very simple construction. And if you see that same structure from a different angle at that packaging facility, you can see those dead ends coming down right into the cable tray, and then we go into the facility itself underground. So this is a way to expand that facility, which was otherwise impossible. So in summary, we've got 7 a year, 7 continents, over 75 countries. It's a viable, it's a safe method, it's cost effective, medium voltage, industrial supply alternative. And the participants of today's webinar may request a certificate of completion to submit to your PE boards for CEO credit by either contacting your local Hendrix representative or emailing Kristen Vanderwall at marmonutility.com.
Okay, thank you very much. Appreciate that presentation. Good, short and sweet. We have a question here. Brian, what about pole size, span, length, and sag? will that be different from typical bare conductor pole sizing, span length, and sag, especially if you consider application in Canada, where we have heavy ice load in the winter?
Yeah, great question. So, you know, I would design, as a design engineer, I would go about designing my line in Canada the same way I would go about designing a line in Florida or the Caribbean or Asia. I would take a look at what span lengths were convenient for me, what my staking engineers wanted. I would simulate that line using, say, PLS CAD or SPIDA, and then that, whether I had one line on that pole line, one circuit on that pole line, or 10 circuits on that pole line, I would model that in PLS CAD or pole CAD or what have you, and that would tell me what kind of pole I need. It's not like guesswork. It's all scientific. We know how to model this in PLS CAD, PLS pole, or the other modeling techniques that we use, and we can either tell you what pole you need or verify the poles that you think you have already selected. In any case, this design work is part of is the work that we do, and we can design that 100% for you, number one. Number two, be with you on site when that line is being built, and that's all included in the project, in the one price system.
Okay, I have another question here. Is there a limit on how many circuits can be on one pole?
Good question. So as of today, we've only had up to 12 circuits on one pole. We have a client designing one with 16 circuits. So theoretically, there is no limit to I mean, I could put 100 circuits on that pole. It might be a little bit tall, but theoretically, there's no limit to the number of circuits I could have on a pole.
Okay, are there voltage limitations for spacer cable?
We're only going up to 115 kV. So again, we have every voltage class from 5 kV to 115 kV. So that would be our limitation. We see getting into 138, 145, and 230. Those are the next generations, but we don't have those yet.
Okay, another question here. Do you have data for your system modeled to use with SPIDA?
We have used SPIDA with some of our clients, say, you know, Southern California Edison.
Maybe you could explain what SPIDA is.
Yes, SPIDA is another. It's like SIME. It's like PLS CAD. It's a modeling program.
Okay.
So yes, we can help you. Either we have the SPIDA files or we can help you develop them. But yes, our people, I don't think we own SPIDA yet, but our design department usually uses PLS CAD.
Okay, do you allow for extra radial ice to be resilient to extreme weather due to climate change?
Well, yeah, we're able to model as much ice as you want on that conductor in PLS CAD, and that will get back to how sturdy a pole you need. If you're anticipating more ice in the future, I know that National Electric Safety Code is changing their wind and ice loadings due to, I guess they're looking at due to climate change. I know CSA is looking to change their wind and ice loading due to climate change. But yeah, I mean, if I tell PLS CAD I have a ½ inch ice, or if I tell PLS CAD I got 4 inches of ice, the same calculations are done. It's just going to change the type of pole that I need. So okay. Do we have that capability to do that? Absolutely, positively.
Great, and that all improves the reliability of our system.